Wouldn't it be nice if we can find the limit of every function simply through direct substitution? Fortunately, or unfortunately, depending how you look at it, substituting the limit directly into the function will oftentimes give you a 0 over 0 expression, which we call an indeterminate, because you can't determine the limit in this form. So in this lesson, we're going to go over a strategy for finding limits when you're in this situation. So the theorem we'll use goes like this. If we're looking for the limit of a function f of x as x approaches some real number c, and we can find another function, g of x, that has all the same values except for where x equals c, then we can say the limit of g of x as it approaches c is equal to the limit of f of x as it approaches c. You may be wondering, what's the point of this? How can two different functions agree everywhere except for the point of interest? Well, let me remind you, limits don't care what happens at that point, c. It only cares about what happens as you approach c. Let's look at this through an example. Let's take the limit of x cubed minus 1 over x minus 1 as x approaches 1. Notice if we substitute 1 into this function, we get a 0 over 0 expression, which is indeterminate. But this also means that they have a common factor of x minus 1. So let's factor out x minus 1 from the numerator. We're factoring the numerator as a difference of cubes. Now we can divide out the like factors. And now we have our new function g of x, which have all the same values of f of x, except for at x equals 1. Here's what those graphs look like. On the left is our original function, f of x. And on the right is g of x. Notice they're the same everywhere, except for at x equals 1. That means the limit is the same as x approaches 1. In g of x, we can use direct substitution. So plugging in 1 where we see x, we get 1 squared plus 1, which simplifies into 3. So the limit of our original function, f of x, as x approaches 1, is 3. You might be wondering, well, couldn't we have graphed our original f of x function and we could have avoided all of this? Because from the graph, you could see that as x approaches 1, the function approaches 3. So you're right, we can use graphs to reinforce our calculations when using this method. But be careful, because sometimes our graphing calculators are limited, especially when these calculators are trying to graph limits. Sometimes they'll give you misleading graphs. One thing to keep in mind as you use this strategy is to remember that not all functions have a limit as x approaches c. For example, the limit of x cubed plus 1 over x minus 1 as x approaches 1, the limit does not exist. That graph looks something like this. Where we have a vertical asymptote at x equals 1. Why don't you try one? Let's take the limit of x squared plus x minus 6 over x plus 3 as x approaches negative 3. So pause the video and apply the theorem from this lesson to find the limit of this function as x approaches negative 3. Again, notice substitution fails. We get 0 over 0 indeterminate form. So let's factor out an x plus 3 from the numerator. So we're going to get x plus 3. We know that's going to be one of the factors. And the other one has to be x minus 2. Because the difference has to be 1, and the product has to be negative 6. Now we can get rid of the x plus 3's, and we have our function, g of x, which agree at all points with f of x, except for at x equals negative 3. The function of g of x, and I'm sorry, let's say this is f of x. F of x and g of x agree everywhere except for at x equals negative 3. But we don't care what the value is when x is equal to negative 3. We only care about what the value is as it approaches negative 3. So now let's directly substitute negative 3 into g of x, and we'll get negative 3 minus 2, which is negative 5. So negative 5 is the limit for both functions g and f as x approaches negative 3. And by the way, that graph looks something like this. That's supposed to be a straight line. Now, in our original function, there's a hole here. So maybe I should put an open circle at negative 3, negative 5. And g of x will look the same, except that hole is filled.